Welcome to an extraordinary debate that transcends time, between two of the greatest minds in physics, Albert Einstein and Stephen Hawking. Through advanced artificial intelligence, we've simulated a dialogue that explores their ideas, perspectives, and theories on the very fabric of the universe. In this four-part conversation, our legends will discuss time, black holes, the elusive theory of everything, and humanity's future in the cosmos. In this first segment, we dive into the fabric of reality, time itself. What is it, truly? A dimension? An illusion? A direction? Einstein and Hawking both revolutionized our understanding of time, but they saw it from different angles. Let's hear them.
Time is not what our senses tell us. It is not a flowing river but a coordinate, just like space. When I developed special relativity, it became clear that time dilates with motion and slows near gravity. Think of GPS satellites. Without time corrections predicted by relativity, they would be off by kilometers each day. Time is relative, not universal. There is no now that applies to all observers.
True, relativity shows time is flexible. But I see another layer. Time has a direction, from past to future, and that's tied to the second law of thermodynamics: entropy increases. That arrow of time governs how we remember the past but not the future. My research on black holes suggested that even there, entropy plays a vital role.
Entropy gives time its direction, but it does not define its nature. The equations of physics, whether Newton's or Maxwell's or even my own, work just as well forward or backward. Time feels like it flows because our brains interpret causality in one direction. But in spacetime, all events simply are. The distinction between past and future is psychological.
Yet, the universe had a beginning, a singularity. That singular point marks the start of time as we know it. I proposed that near the origin, time might become imaginary, not imaginary as in fake, but perpendicular to real time, like how imaginary numbers work in math. In such a model, time is curved and finite but has no edge. So, perhaps the universe didn't begin in a classical sense. It just exists.
That's a fascinating idea, Stephen. If time indeed curves like space, perhaps the universe is a self-contained entity, no need for a creator or external clock. Yet I remain cautious about imaginary time. Mathematics is a powerful tool, but not every solution has a direct physical meaning.
Of course, mathematics must be tied to observation. But remember, the idea of curved spacetime was once seen as abstract too, until Eddington's 1919 eclipse showed stars bending around the sun. Imaginary time helps us avoid singularities and paradoxes. It's not just mathematical convenience, it may describe the real geometry of our universe.
From relativity's warping of time to the quantum proposal of imaginary time, this conversation stretches our very understanding of existence. Einstein views time as a relative coordinate shaped by motion and gravity, while Hawking sees time as directional, born from entropy and possibly curved in imaginary dimensions. One sees time as an illusion, the other sees it as a dynamic field emerging from the chaos of creation. But both agree, time is far stranger than we ever imagined. Now we descend into the densest mysteries of the universe, black holes. Where matter collapses, and physics breaks. Both Einstein and Hawking shaped our understanding of these cosmic beasts. But they disagree. Can information ever escape a black hole?
According to my general relativity, black holes are regions where gravity is so intense that nothing, not even light, can escape. The event horizon marks the point of no return. What falls in is lost to the outside universe. My equations don't speak of information, they describe geometry. Once inside, the singularity awaits, a point of infinite density where the laws of physics break down.
But that's exactly the issue, Albert. If information truly disappears, it violates quantum mechanics, which demands that information be preserved. I showed in 1974 that black holes emit radiation, now called Hawking radiation. Over time, they evaporate. The paradox is, what happens to the information that fell in? Does it vanish, or is it somehow encoded in the radiation?
I must admit, your discovery of black hole radiation was revolutionary. Yet I remain skeptical of mixing quantum theory with general relativity without a unified framework. My equations weren't built to accommodate information flow in this way. Perhaps what we see as a paradox is simply a limitation of current models.
But ignoring it doesn't make it go away. I believe black holes do destroy information, at least in a classical sense, but that breaks fundamental symmetries in physics. Later theories, like the holographic principle, suggest information is stored on the event horizon itself, like a cosmic data disk. What if the surface holds the secrets of everything inside?
That notion, that a 3D reality can be projected from a 2D surface is bold. But so was my idea a century ago, that gravity is not a force but the curvature of spacetime. Maybe this is another leap. Still, I'd caution, without experimental proof, we tread on speculative ground.
Speculation, yes, but rooted in mathematics and guided by quantum logic. Recent advancements in string theory and quantum gravity support this idea. We must push theory where experiment cannot yet reach. Information may not be lost, it may just be scrambled beyond recognition.
Einstein sees black holes as eternal prisons, final endpoints of matter and mystery. Hawking challenges that finality, arguing that information fights to escape, perhaps hidden in subtle radiation or holographic shells. The paradox remains, but the debate propels physics forward. From a singular point of infinite density to a vast cosmos teeming with galaxies, how did it all begin? Einstein and Hawking offer radically different lenses, geometry versus quantum singularities. Let us journey to the dawn of time.
My equations allow for a dynamic universe, expanding or contracting, but I originally resisted that idea. I introduced the cosmological constant to maintain a static cosmos. However, later evidence from Edwin Hubble confirmed the universe is expanding. This was in line with Friedman's solutions to my equations. Still, I envisioned the universe as a continuum governed by geometry and smooth evolution, not a sudden explosion.
Yet the evidence points toward a beginning, the Big Bang. A moment when all matter and energy were compressed into a singularity. But classical physics breaks down at that point. That's why I proposed a no-boundary condition. The universe may have no edge in time, like the South Pole is not the beginning of Earth. Time itself could emerge from a quantum state, blurring the distinction between before and after.
Your proposal is elegant, Stephen, mathematically beautiful, yet conceptually challenging. I wonder, if time emerged from such a state, what mechanism determined its direction? My relativity treats time as one of four coordinates, reversible in theory. But entropy, the arrow of time, gives it direction that remains mysterious.
Indeed, entropy is key. The universe started in a highly ordered state, and as it expands, entropy increases, time flows forward. But why did the universe begin in such a low entropy state? Some theorize it's a quantum fluctuation in a timeless void. Others suggest a multiverse, infinite beginnings. My goal is to reconcile quantum cosmology with observable physics.
I respect your approach, even if I prefer deterministic models. The unpredictability of quantum beginnings still unsettles me. Yet, as we peer deeper into the cosmic microwave background, perhaps data will one day favor one picture over another.
And that's what drives science, Albert, models competing for truth. The birth of the universe may lie beyond direct observation, but not beyond reason.
Einstein envisions a smooth unfolding of spacetime, resisting singular beginnings. Hawking dives into the quantum unknown, where time itself may be born from nothing. The origin remains veiled, but each theory adds light to the cosmic dawn. Will machines surpass human intelligence? Could artificial minds outthink, outperform, even outlive us? In this final round, Einstein and Hawking confront the ethical and existential dimensions of AI.
I have warned that the development of full artificial intelligence could spell the end of the human race. AI, once self-improving, could evolve beyond our control. If aligned with our goals, it could eliminate poverty and disease. But if misaligned, even unintentionally, it could become a force we cannot stop.
Your caution is well placed. Though I did not live to see digital computation rise, I imagined that human tools might one day escape our hands. The danger lies not in intelligence itself, but in ambition without wisdom. Technology advances faster than moral development. This imbalance can be catastrophic.
That's precisely why we must embed ethics and transparency into AI from the start. Explainable algorithms, accountable creators, global cooperation, these are not luxuries but necessities. Without oversight, the competitive race for AI dominance could lead to outcomes we don't intend or even understand.
Indeed, the arms race mentality, even in science, is dangerous. When I urged Roosevelt on the atomic bomb, it was out of fear that others would build it first. Yet I saw what followed with regret. AI is similar. Once released, it spreads beyond borders. We must learn from our past.
Still, I remain hopeful. Imagine a future where AI helps us colonize Mars, solve climate change, decode the brain, or even simulate entire universes. But we must guide this tool with global dialogue and deep foresight.
Hope is necessary, but not sufficient. True progress requires reflection. We must ask, what kind of future do we want, not just what we can build? If AI reflects our best selves, it may indeed become our greatest ally.
In their final exchange, Einstein and Hawking converge on a singular truth: the future is unwritten. Artificial intelligence holds immense promise and profound peril. Its destiny will not be shaped by machines alone, but by the minds and morals of those who create them. As the debate ends, one question echoes beyond the studio: will AI elevate humanity to new heights, or erase us from the story of the cosmos? The answer begins with you.